we shall close this discussion about the integration and we will move to the next topic, namely that we will start discussing what is called sequences and series of functions. Again, you are already familiar with sequences and series of numbers. Okay. So all that we do here is that replace the numbers by functions. Okay. As you know, let us begin with the definition. As you know, sequence is a function whose domain is the set of all natural numbers. Okay. Codomain can be anything. Okay. When codomain is a real number, we call it sequence of real numbers. If it is complex number, it will be sequence of complex numbers. So similarly, you can talk of sequence of anything, sequence of matrices, sequence of vectors, and also sequence of functions. Okay. So sequence of so the functions defined where? Okay. Of course, you can to be very general, we can say that each function is defined on different sets, but with that kind of thing we will not be able to do anything further. So we shall just fix one set. Let us say E is some non-empty set, and we shall assume that all functions are defined on this set E. Okay. Quite frequently this set E will be subset of some metric space, okay, and in most of the application it will be some interval in the real line, okay, closed and bounded interval on the real line. Okay. So for each n in n we have a function fn. Let us say real valued function fn from E to R. Okay. Then this fn is a sequence of functions. Fn, this is a sequence of functions. Okay. All right. Now what do we do with this sequence of functions? Several things. Okay. Once you have a sequence of functions, then if you take any x in E, then this fn of x is a real number. Okay, fn of x is a real number. So if you let this small n vary over big N, then that will be a sequence of real numbers. Okay, so fn x is a sequence of real numbers. This is a sequence of real numbers. Okay, and you already know what is meant by saying that a sequence of real number converges or diverges, etc. Okay, right. So now if it so happens that for each x in E this converges, okay, then it will mean that, and suppose it converges to some real number, then that will define a new function from E to R. Okay, because for each x you have a new number which is a limit of this sequence. Okay, so let us say if we can say that if fn x converges for each x in E, then we can define a function f from E to R, function f from E to R given as follows, that is f of x is nothing but limit of fn of x. Limit as n tends to infinity. Okay. And when this happens, we say that the sequence fn converges to the function f pointwise. Okay. When that means for each x, that is for every x in E. Okay. We describe it as follows. We say fn tends to f pointwise. Okay. What is the meaning of this? It means that for each x the sequence fn x of real numbers converges to the real number fx. Okay, that is the meaning of this is the following. Okay, that is fn x converges to fx for every x. Okay. Okay. Similarly, one can, okay, now before proceeding further, just to, in fact you you have come across such sequences of functions and consider their pointwise limits also, but maybe perhaps without explicitly mentioning that that is a sequence of functions. Okay. For example, let us just take this case to begin with. Okay. Suppose we take E as, let us say, the interval 0 to 1 and define f and x as, okay, to begin with let me say just x to the power n. So for 0 less than or equal to x less than or equal to 1. Okay. This is a very standard and well known example. Okay. So what happens in this case, when you fix x, when you fix some x, then f n x is the sequence x to the power n. Consider various cases. For x equal to 0, this will be 0. If x is less than 1, that limit will go to 0. If x is equal to 1, it becomes a constant sequence 1. Okay. So we can say that suppose you define f x equal to 0 for 0 less than or equal to x less than 1 and equal to 1 for x equal to 1, then f n converges to f pointwise. Okay. That is about the convergence of the sequence of functions pointwise. Okay. Now just as we can talk about the sequences, in a similar way we can talk about the series. Okay. Just as in the case of real numbers, you know that everything that you want to say about the series is said in terms of the sequence of partial sums, right. So do the same thing here. Given, suppose I want to talk of a series, let us say sigma fn. Okay. Then look at its partial sums. Okay. Look at its partial sums. So suppose this is Sn, Sn will be now f1 plus f2 plus fn. Okay. Remember, each Sn is a function. Each Sn is a function from E to R. See, by the way, here going back to this example here, since we have taken this set E as 0 to 1, that is why fn converges to f pointwise. Okay. Suppose we take some other set, it may not happen. For example, suppose I take E from 0 to 2, okay, then for x bigger than 1 the sequence fn does not converge. Okay. So it is not necessary that given any sequence it should converge to some function pointwise, or even if you take say minus 1 to 1, what will happen is that it will converge for minus 1 less than x less than or equal to 1. Okay. But if you take x equal to minus 1, then the sequence becomes 1 minus 1 1 minus 1 etc., and then it will be a divergent sequence. Okay. So it also depends on what is this set E, the behavior of the limit, or whether the sequence converges pointwise or not depends on what is this set E. Okay. Coming back to the series, given any such sequence we can think of a series like this, sigma fn, n going from 1 to infinity, or in certain cases it is convenient to take n going from 0 to infinity. It does not matter. Okay. Where you start really does not matter, and this is something that you should know, and perhaps you know about the sequences as well as the series. As far as the consideration of the convergence or divergence of a sequence or a series is concerned, what happens to a first few terms does not matter. A finite number of terms can be removed from a sequence, a finite number of terms can be added to a can be inserted in a sequence or a series. The convergent sequence will remain convergent and divergent sequence will remain divergent. Okay. Of course, if it is a series, the sum will change. Okay. Sum of the series may change, but the convergent series will remain convergent and divergent series will remain divergent. Okay. That the behavior with respect to convergence or divergence will not change by changing a finite number of terms either in a sequence or in a series. Okay. So coming back to this is a sequence of partial sums. Okay. So this Sn is a sequence of partial sums, this is a sequence of partial sums. And so this is a sequence of functions. Okay. Each Sn is a function. So we have already defined what is meant by saying that a sequence of function converging pointwise. So if this sequence Sn converges to some function, suppose that function is g, then we say that the series sigma fn converges pointwise to that function g, and in that function g is called the pointwise sum of this series, okay. So that is the idea, okay. So so let us just so if Sn converges to G pointwise, we say that sigma Fn converges to G pointwise. Okay, we say that sigma Fn converges to G pointwise, okay, and G is called the sum of the series, okay. So this G is called and denoted by this sigma Fn n going from 1 to infinity is equal to G, okay. So G is called the sum of, in fact one should say pointwise sum, because everywhere we are calling pointwise convergence, so we should say pointwise sum, but okay, it is not very strictly adhered to, okay. The sum of this series sigma Fn. Okay. All right. So this is as far as the definitions are concerned. Okay. Now what are the kind of problems that we are interested? Okay. The problems are as follows. What we want to know is that given a sequence or a series, suppose each Fn has some property. Suppose each Fn has some property, then does the sum also have that property? Does the limit also have that property, or in this case does the sum also have that property? What are the properties? Usual properties that we are interested in analysis or calculus, for example continuity. Okay, the kind of question that we are going to ask is, suppose each Fn is continuous, okay, does it follow that F is continuous, or in this case suppose each Fn is continuous, does it follow that G is continuous, okay. And similarly about the differentiability, okay, suppose each Fn is differentiable, does it follow that F is differentiable, and analogous question about the series, okay. And suppose each Fn is integrable on the interval, suppose E is the interval a to b, suppose each Fn is integrable on ab, can we say that F is also integrable on ab, etc. Okay. Now when we start analyzing these questions, it turns out that this pointwise convergence is not a very satisfactory thing, okay. You already have one example here, okay. Here each Fn is a continuous function, but this F is not a continuous function, okay. And in order to understand what exactly is happening here, you can understand that this question basically means whether we can interchange certain limits. In each such question some two or more limits are involved. If they are taken in a particular order you get one value, if they are taken in some other order you take other value, and the question is whether those two limits can be interchanged. Let us illustrate this, okay. Suppose we take this question, that is, let us say Fn converges to F, okay. Let us look at here, okay. Suppose, so to talk of the continuity we have to take this set E as in some metric space, okay, for the, so let us say that E is in some metric space. Suppose XD is a metric space, E is a subset of some X, okay, where XD is some metric space, and let us say some X is in E. What is the question? If each Fn is continuous on E, okay, suppose that is the question, if each Fn is continuous on E, and Fn converges to F pointwise. Okay, then the question is does it follow, does it imply that is F continuous? But this is a question which we already answered by looking at this example, okay. What I wanted to say is that this, or answering this question, essentially involves interchanging the order of some two limits. So that is what I want to illustrate now, and what exactly it means, okay. Let us take some point x in E. What is the meaning of saying that x is continuous at E? suppose you take limit x is f is continuous at E means you take limit of f of let us say f of t as t tends to x, that should be same as fx, right. So that okay, f is continuous at x what is the meaning of this? This means, okay, let us say this is same as saying that limit of let us say f at t as t tends to x is equal to fx, okay, alright. Now let us also use the fact that f is a pointwise limit of fn, okay, that is for each x in E or each t in E, f of t is same as limit of fn of t, right. So this left hand side, if suppose I put that here, f of t will be nothing but is limit of n tends to infinity fn of t. So that is, this is same as saying that limit as t tends to x and limit as n tends to infinity of fn of t, okay, this is equal to fx, that is if f is continuous at x means this, right, f is okay. But what is fx? Fx is limit as n tends to infinity of fn of x, okay. So this is same as limit of fn of x as n tends to infinity, okay, right. But we have assumed that each fn is continuous, okay. So I can replace that fn x as limit of fn t as t goes to x. So I can say that this is same as limit as n tends to infinity limit t tends to x of fn of t, okay, okay. So just look at the first and last, okay, just look at the first and last, okay. Let me rewrite that here. Okay, what is the left hand side? Limit t tends to x, then limit n tends to infinity fn of t. This should be same as limit n tends to infinity limit t tends to x fn of t. Okay, do you agree? So to say that f is continuous at x where f is a pointwise limit of fn, it's same as saying whether you can interchange these two limits. What are the limits? Remember the quantity is same fn of t everywhere, okay, and limits whether you take first let t tend to x and then let n tend to infinity, or whether you first let n tend to infinity and then let t tend to x, whether these two processes can be interchanged, okay. So asking whether f is continuous at x is basically asking whether these two limiting processes can be interchanged, and practically every question which I have said so far can be brought into this form, whether it is a question of differentiability, whether it is a question of integrability, because each of these questions, see whether it is a derivative or integral, all these are some limits, okay. So each of these questions basically can be transformed into questions like this, whether certain limiting processes can be interchanged, okay. And from your experience you should know that in general the answer is no, okay, unless you put some additional restrictions we cannot in general interchange the way in which you take the limit, okay. Again let us take a well known example. Suppose you have something like this, okay, suppose you take something like m by m plus n where m n both are natural numbers, okay. This is a function of both m and n, okay. So you can first and we can consider the limit of this as m goes to infinity and n goes to infinity in two ways, okay. First let m tend to infinity and then whatever you get let n tend to infinity, and the other way, okay. Let us see what happens. Suppose you first take limit of this as m tends to infinity, then what will be that? n is fixed and we are letting m tend to infinity, okay. So limit will be 1, okay, limit will be 1, okay, alright. And then after this if you let n tend to infinity, so suppose I say limit n tends to infinity and limit m tends to infinity m by m plus n, this will be same as 1, okay, alright. Now look at the other way, suppose I take limit n tends to infinity of m divided by m plus n, m is fixed, okay, and n is going to infinity. So what will be that limit? That is 0, right, that is 0, and that is independent of whatever is m, okay. For every m this limit is 0. So if you now let m tend to infinity, you are going to get 0, right. So limit m tends to infinity and limit n tends to infinity of m by m plus n, that is 0, okay. So the same quantity m by m plus n, if you take the limits in two different orders, you may get different limits. Of course in some cases the limits may be the same, but you need some extra conditions for that, okay. So that is what we are going to consider now. What are the extra conditions? Means we will talk of some different kind of convergence which is supposed to be stronger than this convergence, and if under that convergence these properties are preserved, okay. That is, if each fn is continuous then f is continuous, etc., okay. And that this is one way, okay, that is one way of dealing with is that you strengthen the concept of convergence, okay. There is also other way of dealing with this question, okay. You can weaken the concept of integrability, okay, right, but that is something we will not follow, okay. That is something you will do in your next course on measure and integration, okay, where you will think of different types of integrals and where even pointwise convergence also will be fine for looking at the integrals. Now one more thing, that is when we come to the integrals, it is not just the question of integrability that we are interested in. We would also want to know that suppose we take a series like this, okay, whether such a series can be differentiated pointwise term by term, that is if sigma fn converges is equal to g, can we say that sigma fn prime is equal to g prime, or can we say that sigma integral of fn is equal to integral of g, etc., even that kinds of questions, and it is those questions which are very important in this convergence that we are going to consider. Now before proceeding further, let me just give one more example to illustrate that things are not very good when with respect to pointwise convergence, even when we talk of integrability, okay. Okay, I will not give all details, I will give some of these things to you as an exercise. Take fn x as, so let us say n times x multiplied by 1 minus x square raised to n for 0 less than or equal to x less than or equal to 1, okay. Okay, I will not go to all the details, show the following, okay, I will just give this as an exercise, okay. Show that fn tends to 0 pointwise on 0 to 1, okay, right. And remember this is a continuous function, okay, since continuous function on 0 to 1 and hence integrable, okay, continuous and hence Riemann integrable, okay. So integral 0 to 1 fn x dx exists, for this Riemann integral exists, okay, okay, but this does not go to the integral of this function will be 0, okay, integral this, so this does not converge to 0, okay, this does not converge to 0, okay. Try to show that on your own, we will not spend, this is simple, okay, you have to just calculate this integral, that will turn out to be some function of n, and you show that that sequence does not go to 0, okay, alright. Okay, so the new convergence that we are going to discuss is what is called uniform convergence. Uniform convergence. Okay, what is the meaning of this? Okay, let us first give the definition and then we will try to explain what is happening here. Okay, so suppose let us say that let Fn from E to R be a sequence of functions and f is also a function, okay, and f from E to R is also a function, be a function. Okay, we say that Fn converges to f uniformly. Okay, that is what we want to define. We say that Fn converges to f uniformly. Fn converges to f uniformly. Again, as like any convergence or any limit, this definition is in terms of epsilons, etc. So if for every epsilon bigger than 0, okay, we are talking about the sequences. Okay, so if for every epsilon bigger than 0 there exists some n0, there exists some n0 in n, okay, such that for every n bigger than or equal to n0 something should happen. Okay, for every n bigger than or equal to n0 something should happen such that there exists n0 in n, such that for all n bigger than or equal to n0 what should happen is that mod fnx minus fx, this is less than epsilon, mod fnx minus fx less than epsilon, and this should happen for every x in E. Okay, such that for all n bigger than or equal to n0 mod fnx minus fx less than epsilon for every x in E. Okay. Okay. Now suppose you had taken some x in E, okay, and you had said that for every epsilon bigger than 0 there exists n0 such that whenever n is bigger than or equal to n0 mod fnx minus fx is less than epsilon. Okay, then that would mean that fnx converges to fx, right, that would mean that fnx converges to fx, and since this is happening for every x in E, that means that fnx converges to fx for every x in E. So if fn, or in other words it is same as saying that if fn converges to f uniformly then fn converges to f pointwise also. Okay, that is, so that is an elementary observation, but usually it is given as a theorem. So if fn converges to f uniformly then Fn converges to f pointwise. That means uniform convergence is stronger, uniform convergence is stronger than pointwise convergence. Then there is an obvious question, what about the converse? Okay, that is, can we say that if Fn converges to f pointwise then it converges uniformly? Okay, if that were true, obviously then it will mean that both the notions of convergence coincide. Okay, that is not the fact. Okay, so the converse is false. Now how does one show that the converse is false? There is only one way. Okay, that is, you have to construct a sequence of functions which converges pointwise but not uniformly, right, that is the only way. Okay, okay. We shall do it, okay, we shall do it in the course of time because that will require some more work, so I will not go into that right now, okay. So this is about the okay. Now what exactly is the difference? See, when you say Fn converges to F pointwise, let us just look at this, okay, and compare the two definitions. What is the meaning of this? Fn converges to F pointwise, this means, or this is equivalent to saying that Fnx converges to Fx for every x in E, okay. Fnx converges to Fx for every x in E, or that is same as saying that this is equivalent to saying that for every x in E and for every epsilon bigger than 0 there exists n0 in n such that n bigger than or equal to n0 implies mod Fnx minus Fx is less than epsilon, okay, mod Fnx minus Fx, that is the meaning of saying that Fnx converges to Fx, right, okay. Now what is the difference between this and this, okay. See, in this definition when we say we start with some x in E and we look at the convergence only at that point, okay, we look at the convergence only at that point, though it happens at each point, this n0 may depend on this x, because given x in E for this epsilon we say that some n0 exists, but this n0 may in general depend on this x, okay. So if you want you can write it as n0 of x, okay, right. But here we are saying that this n0 that should work for every x in E, okay, that n0 should work for every x in E, okay, that is the main difference, okay. That is, given epsilon you should be able to find n0 such that whatever we are saying happens for every x in E, okay, right. Now what is the meaning of saying that in a pointwise convergence you given x you will have some n0 which depends on that x? If you take different x you will get different sets of different values of n0. Suppose it is possible to take the maximum of all those n0s, okay, then that maximum will work for all x, okay, but this may or may not be possible, okay. If it is possible then that sequence converges uniformly, okay, if it is possible then that sequence converges uniformly, otherwise if it is not possible means what, it means there is no maximum, okay, there is no maximum, that is if you take n0x for different values of x its maximum is infinity, okay, right. So that is, and that is what can happen in case of pointwise convergence, okay, alright. Okay, now this is about the sequences. In a similar way we can talk about the series, okay, because series is after all nothing but the sequence of partial sums. You take the sequence of partial sums, if that converges to a function g uniformly we will say that the series converges uniformly, okay. So let us say now you consider, let us say Sn is equal to f1 plus f2 plus fn, okay, we will say that if Sn converges to G uniformly we say that sigma Fn is uniformly convergent, uniformly convergent. Sigma Fn is uniformly convergent, okay. And we will say that again we may say use the same symbol sigma Fn is equal to G n going from 1 to infinity, but this time we will say that G is the uniform limit, okay, that is G is the sum of sigma Fn but not pointwise but uniformly, okay, right. So in case of series also we can make a difference whether series is pointwise convergent or uniform convergence, and accordingly we can say that G is a pointwise sum or uniform sum, okay. Okay, now again you look at this definition of uniform convergence. We want to interpret it in a slightly different manner. Okay. What we have here is that for every n bigger than or equal to n0, what should happen is mod fnx minus fx is less than epsilon for every x in E. Okay, so suppose I take this set of mod fnx minus fx for every x in E. Okay, I will just take this set mod fnx minus fx for x in E. Okay. This is a set of positive or non-negative real numbers, right? This is a set of non-negative real numbers. Each of this is less than epsilon. Okay, each of, because this is less than epsilon for every x in E. Okay, that means this is a bounded set. Okay, this is a bounded set. So I can look at its supremum or least upper bound. Okay, so suppose I call that as, let us say, m suffix n. Okay, let m suffix n be the supremum of this. Supremum of this set. So mod fnx minus x belongs to E. Okay, right? Okay. Then what does this say? That this mn is less than epsilon. Okay, mn is less than epsilon for n bigger than or equal to n0. Okay, right? Or suppose you rewrite this definition, what it will mean is for every epsilon there exists n0 such that wherever n is bigger than or equal to n0, this mn is less than epsilon. Okay, so mn is a sequence of real numbers. Okay, so what is the meaning of saying this? That for every epsilon there exists n0 such that wherever, it is same as saying that mn converges to 0, right? Mn converges to 0. So saying that fn converges to f uniformly is equivalent to saying that this sequence of real numbers mn converges to 0. Okay, and that is a very useful criteria in deciding whether a certain sequence converges uniformly or not. Okay, so let us just record that. So fn tends to f uniformly. This is equivalent to saying that mn tends to 0 as n tends to infinity. Okay. And this is something which will be useful in many practical problems. That is, suppose you are given a sequence fn and suppose you are asked to check whether that sequence converges uniformly or not, then the best thing to do is try to find out mn, if not mn, some value or something which is bounded by mn, etc., some estimate of mn. Okay, and then try to conclude from that whether the sequence converges uniformly or not. In most of the cases you will be able to find mn, because see in many practical problems which you come across, this fnx, fx, those all will be continuous differentiable functions in some interval. You can always find the maximum value of that by using methods of calculus and calculate mn. Okay, so that is always possible. Okay, let us look at the example which we had taken earlier. Okay, let us take this example, fnx is equal to x to the power n for 0 less than or equal to x less than or equal to 1. Okay, and what was fx in that case? Fx was 0 for 0 less than or equal to x less than 1 and equal to 1 for x is equal to 1. Okay, all right. Okay, so what will be mn? Mn is supremum of, suppose I take this same definition, mod fnx minus fx, okay, for x in 0 to 1. Okay, all right. Since fnx is defined by the same formula for every x, I will just replace this by x to the power n here. Okay, x to the power n minus fx. Okay, okay, all right. And what is this fx? Fx is 0 for 0 less than or equal to x less than 1. Okay, and it is 1 for x equal to 1. X equal to 1. Okay, at x equal to 1, what happens? This is also 1. Okay, so it is 0. Okay, so I can say that this supremum is nothing but supremum of this x to the power n for 0 less than or equal to x less than 1, right? this is, you can say this is same as supremum of x to the power n for 0 less than or equal to x less than 1. Okay. Okay. All right. And what is this supremum? 1. Is it obvious to everybody that if you take any n, if you take any n and look at x to the power n and find its maximum supremum between 0 to 1, then this is nothing but 1. Okay. Right. So Mn is equal to 1 for all n. So does this happen then? Mn. Okay. So it is clear that this sequence Fn does not converge to F uniformly, right. So Fn, we have already seen that Fn converges to F pointwise, but Fn does not converge to F uniformly, right. Okay. And that is what answers this question. Here we ask whether the converse of this is true. Okay. And now we have an example of a sequence which converges pointwise but does not converge uniformly. Okay. All right. Okay. Now there is one more way of looking at this whole uniform convergence, and that is something which should be of interest to you because you have learned so many properties of metric spaces. So what we can do is that we can take this set E and let me define this set B of E. Okay. What is B of E? Let us say that it is the set of all bounded functions from E to R. Okay. B for bounded. Okay. So B of E is this set of all f from E to R and f is bounded. Okay. Okay. Now there are several properties of this set B of E. It is a set of functions. Okay. It is a set of functions. Okay. Defined on the same set E, and all that we are assuming is that each of this function is bounded. Okay. All right. Now let us view this set from the point of view of some properties of linear algebra. Is this a vector space? In fact this is a well known example of vector space, because all that you need to check is that if f and g are bounded, f plus g is bounded, alpha times f is bounded, etc. Okay. So B of E is a since all functions are going to R, this is a real vector space. Okay. B of E is a real vector space. Okay. Okay. One more thing. Suppose you take this some f in this B of E. Okay. I can look at this number supremum of mod fx for x in E. Okay. We assume that f is bounded. Okay. F is in B of E means f is bounded. So this is a bounded set, and hence this supremum exists as a finite real number, in fact non-negative real number. Okay. Okay. And we will denote this as follows. This is read as norm. We have defined this earlier. Norm suffix infinity is defined as supremum of mod fx where x in E. Okay. Okay. Then this is a norm on this vector space. What is the meaning of this? There are several properties of a norm which we discussed in one of the earlier classes, namely that this is always bigger than or equal to 0, and this is equal to 0 if and only if f is 0. F is 0 means what? It is a constant function 0. Okay. And then norm of alpha times f is same as mod alpha times norm f. Okay. And norm of f plus g is less than or equal to norm f plus norm g. All these properties are very easy to prove in this case. Okay. So we'll simply say, I'll simply just record this, that norm is a norm on B of E. Okay. Okay. then let me again remind you that we have shown that if something is a norm, then that norm induces a metric, okay, that norm induces a metric on this side. And what is that matrix? It is distance between f and g is defined by norm f minus g suffix infinity, norm f minus g suffix infinity, okay. And this is also usually denoted as d suffix infinity, okay, also denoted as d suffix infinity, just to emphasize that this is a norm given by a supremum, okay. This is a norm given by a supremum. So this b suffix b of e along with this metric is a metric space, okay, all right, okay, okay. Now come back to the definition of uniform convergence, okay, and look at this last part, okay. What does it say? That fnx minus fx less than epsilon for every x in E, and this Mn is nothing but the supremum of that, okay. So this Mn is nothing but d fn f, right, d or in our case d suffix infinity, okay, d fn, distance between fn and f, okay, okay. So what does it mean? Suppose something was a metric space with metric d, and suppose you take any sequence in that metric space, and suppose you want to say what is meant by saying that that sequence converges, okay, then what you would have said that given any epsilon there exists n0 such that whenever n is bigger than or equal to n0, distance between fn and f is less than epsilon, okay, right. That is what exactly is happening here, okay, that is what exactly is happening here with respect to this distance, with respect to this distance. In other words, uniform convergence is nothing but the convergence in this metric, okay, uniform convergence is nothing but the convergence in this metric induced by this supremum norm, okay. Is it clear? Once this fact becomes clear, you will try to understand many other results in a different way, okay, alright. So let us take one more thing, which is again a very famous theorem about uniform convergence, known as the Cauchy's criteria for the convergence. Okay. Okay. Now, before going to that, in analogy of this, we will also say, for example, in this metric space, when will you say that a set is bounded? In any metric space, we say that the set is bounded if its diameter is finite, okay, if its diameter is finite, okay. So suppose you take a certain sequence fn, we will say that fn is bounded, if you take distance between fn and fm, then that is bounded by some finite number, okay. So such a sequence is called uniformly bounded, okay, such a sequence is called uniformly bounded, okay. Uniformly bounded means what? Okay, let me recall the classical definition. We will say that fn is said to be uniformly bounded if, okay, there exists some number m bigger than or equal to 0 such that mod of fnx less than or equal to m for every x in. In fact, this is something we can talk about, not only just the sequence but any set of functions, okay, any family of functions. We will say that it is uniformly bounded if this mod fnx is less than or equal to m for every x in E. Now coming back to this terminology, is it obvious to you that this is same as saying that this norm of f is less than or equal to m, norm of fn suffix infinity is less than or equal to m, okay, because norm is nothing but supremum of this mod fnx, okay. Now if norm is less than or equal to m for every element here, if you take any two elements, is it obvious that the distance between them will be less than or equal to 2m? Suppose you take f and g, norm of f minus g will be less than or distance between f and g will be less than or equal to norm f plus norm g, so that will be less than or equal to 2m. So saying that uniformly bounded is nothing but saying that bounded in this metric, okay, saying that a family of functions is uniformly bounded is exactly same as saying that it is bounded in this metric, okay, alright. So what I was saying is that we will want to think of what is called Cauchy's criteria for uniform convergence. Cauchy's criteria for uniform convergence. Uniform convergence. Okay. Since the clock indicates that the time is over, we will not go into the discussion of the exact details of this, but what I want you to understand is that we shall state and prove this theorem, and what it will mean basically is to show that this metric space is complete, okay. What we will basically show is that if you use the language of metric spaces, I can simply say that this is a complete metric space, okay, but we will see that in the next class.